Alright, well, welcome back. This is the second time I've had to record this video because the first time around I had some technical difficulties with my microphone. Swapped computer and things appear to be fine now. Today we're going to look at place value. I just want to double check first and foremost that you've made some good progress with your tables. So you should be able to answer the following pretty much instantaneously. 7 8s, 6 5s, 9 7s, 8 8s, 4 6s, 12 8s. Pretty much instantaneously. If you are still having trouble with it, then you need to go back and keep practicing those tables. It will become obvious and apparent as to why as and when we proceed through this content. Okay, let's move on. We're going to look at place value today, and that is all about numbers. Numbers exist on a number line between positive infinity and negative infinity. So if you can imagine, this is your number line here. 0 is nothing. To the right of 0, it's the blue section, and that will lead off to positive infinity. And the red section to the left of 0 is negative infinity. Infinity is an abstract term describing a number with no limit. So the way I like to explain that, or to get people to visualize it, is thinking of money. If you had a never-ending income stream, you would be at positive infinity. So if you had that kind of money coming in forever, yes, you would be at positive infinity. Now, if you imagine that same income stream, but not coming into you, but instead being taken away or going out of your pocket, that would be negative infinity. So it's just the transfer of wealth in the opposite direction. That, I think, is the best way of thinking of it. If a number is positive, it will be in the blue section, to the right of 0. If it's negative, to the left of 0 in the red section. A place value table is used to help you determine how large or small a number is. So the decimal point kind of divides the table. To the left of the decimal point, you've got your units, your tens, your hundreds, your thousands, 10,000s, 100,000, millions, 10 millions, 100 millions, billions, 10 billions, 100 billions, trillions, and it goes on and on and on, depending on how many zeros the number's going to have. To the right of the decimal point, you've got tenths, hundredths, thousandths, 10,000th, 100,000th, millionths. And these are for very small numbers. They can either be positive or negative, but you'll see some examples of it in a moment. So I've got some numbers here. If you'd like to pause the video and have a go at putting those numbers onto this place value table, please feel free. And then we'll come back in a second and do it. Okay, here we go. So I'll get a nice blue for this. 303, we have to understand what each of these numbers represent. So this is the number 303. The 3 at the start is our 100, the 0 is a 10, and the 3 is a unit. So I could simply write it in as 303 there, like that. Next we've got 0.0303. So the 0 at the front will go into the units column. And then you would fill in the rest according to where the zeros and the 3s actually are. So there's a 0 in the tenths column, a 3 in the hundredths column, a 0 in the thousandth column, and a 3 in the 10,000th column. Next we're looking at 30.3. 3 here is a 10, That's a unit, and that's a tenth. So it will be 30.3. Next, we've got 3,003,003. So that 3 is your million, this is a unit, and this is a 1,000th. So you can effectively fill in the 3's, decimal point, and then everything else is a 0. This one is very similar to the second one I did. You've got the 0 in front of the decimal point, and then we've got 4 zeros, 1, 2, 3, 4, and a 3. Lastly, this number is 3,030, so that's 1,000, that's a 10. We can put in a 3 here, 0, 3, 0. Done. So with the numbers 303 and 3030, what's missing is a decimal point. It doesn't mean that the decimal point doesn't exist. It's still there, but it's got no relevance because there's nothing to the right of the decimal point. As such, we don't need to include it. But it's useful to know that that decimal point does exist and should still be there. So then what happens when we introduce positive and negative numbers? Again, pause the video if you'd like to have a go. And then I will go through it. So for the moment, I'm just going to ignore the minuses. Okay, I'm just going to fill these numbers in as if they weren't positive or negative. So we got 13.2 first and foremost. That will go in here. Then we've got 420.7. Then 1509.26. Then 0.0343. And finally 2,435.86. So we look at the numbers that have got negatives, which are these ones, and we're just going to put the minus in front. Okay, so that's all there is to it. You are changing the 420.7 from a positive amount to a negative amount. Again, think of it like that infinite, never-ending money supply. If it's coming in, it's going to be positive, and if it's going away from you, it's going to be negative. So sometimes there's a mix of fractions and decimals. You need to be able to determine how large a fraction is in terms of a decimal. To do this, short division is required. So 4 over 7 means 4 divided by 7. And we've covered short division in the first video. 7 into 4 doesn't go. Decimal point goes in. And we're now looking at 7 into 40. How many times does 7 go into 40? This is where our times tables come in. 7, 14, 21, 28, 35. 5 times. 7 fives are 35 with a 5 remainder. another 0 is generated. Now I'm doing 7 into 50. 7 times tables, we know 7 5s are 35, 7 6s is 42, 7 7s are 49. Generates a 1 remainder. 7 into 10 goes once with a remainder of 3. We're now doing 7 into 30. 7 into 30, 4 7s are 28. Remainder 2. And this will continue carrying on. I'm not going to carry on with it. You'll find that it should recur after a certain amount. I think. Let me double check that actually on the calculator. 4 divided by 7. Yes, it does recur after a certain amount, but that's enough for us to know that 4 sevenths is 0.571. Next, we're looking at negative 2 fifths. So, similar deal, 5 into 2 doesn't go. Decimal points. 5 into 20 goes 4 times. And there's no remainder. So, that is 0.4. Except we're forgetting the negative here. That is actually minus 0.4. So, to put these numbers in order of size, starting from the smallest, we have to look at the number that is the most, the least, or to the furthest on the left on that number line, which will be the negative number. It's going to be less than 0, so it will be less to the left. That will be the first one. Next, all of the numbers are positive, so it will be to the right of the 0 on the number line. And the smallest number there is this one, the 0.383, so that's the second number. The next largest one is the 0.4, that's the third one. The fourth one will be 0.457, and 0.571 is in last place. So that's the correct order. 1, 2, 3, 4, 5. We need to spell that out in terms that someone reading this from smallest to biggest will be happy to look at. So the original number was minus 2 fifths in first place. Then we've got 0.383. Then we've got 0.4. Then we've got 0.57. And finally, at last place is 4 sevenths. Okay, that's something you need to be able to do. And I've got a slide here for you to practice that on your own. Here's an old exam question. It's exactly the same as what I've just done. Pen. Yeah. So we need to find out what each of these are in decimals. Then we can write them in order of size, starting with the smallest number. Pause the video, print off the slides, have a go. Okay, we're back. So let's do it. 15 into 7. 15 does not go into 7. But it does go into 70. It will go in how many times? Well, let's try and go through our 15 times table. 15, 30, 45, 60. 4 times. And there's 10 remainder. We're now looking at going into 100. Again, 15 times table. 15, 30, 45, 60, 75, 90. So that's 6 times with a remainder of 10. And 15 into 100 again goes 6 times with another remainder of 10. This is known as a recurring decimal because it will carry on generating 6s all the way for its life. So the way we represent that is like this: 0.46 with a dot above the 6. The dot above the 6 tells us that the 6 will go on and on and on forever. Next, we're looking at 35%. We should know that 35% is 35 out of 100, and that will amount to 0.35. Again, I'm going to go through that in a second. Lastly, we've got 3/7, so we need to do 7 into 3. Doesn't go. So I'm now going to look at 7 into 30. 7 into 30, 7 times tables, 7, 14, 21, 28. 4 down, 2 carried. 7 into 20 goes twice, remainder 6. 0 down. 7 into 60. 7 8s are 56, carry 4. 7 into 40 goes 5 times, remainder 5. And this will go on. I'm not going to go on beyond 4 decimal places, it doesn't seem worth it. But the process is literally times tables. So we're looking at 0.428 here. Let's order these then. The smallest is this one. The next smallest is this one. The next smallest is this one. And then finally we're looking at this one. So, your answer, you should always spell out what your answer is. That's a bit messy, sorry about that. First is 35%. Second is 0.4. Third is 3/7. Fourth is 7/15. Okay, so we're going to look now at inequality symbols. It's really important to know about these. Even if you don't use them, we're not going to look heavily at inequalities. I just felt it's kind of important to know about them, because knowing about the symbology makes life a little easier later on. So starting with just a symbol everyone should know is this symbol. It's the equals sign. It means equals to, so an example of that would be 3 equal to 3. The next one is this equals sign with a line through it. This means does not equal to, so mathematically you can say that 3 does not equal 5. Makes sense, doesn't it, really? Next we've got greater than, so this is where the symbol is pointing to the right. 4 greater than 2 as an example. The opposite way is less than, so 2 will be less than 4. Makes sense, doesn't it? Then you've got greater than or equal to, so that line under the bottom of the greater than or less than means that you've got it as an equality statement. So 3 does indeed equal 3, but also 4 is greater than or equal to 3. They're both true statements with that symbol. Likewise with the opposite way, 2 does equal 2, but 2 is also less than 3. So yeah, the important thing here is on the right hand side we've got examples of statements that you can make with numbers using those symbols. I'm not going to go into it too heavily, but it is important to know that you can make statements with inequalities. And I'm going to make a statement here which I think you'll appreciate, that pepperoni not pepperoni 1. Oh dear. Pepperoni on pizza is strictly greater than Hawaiian. Now that is a bit political because there are millions of people in the Pineapple fan club who will come after me with knives and pitchforks for making that statement. So perhaps it would be a bit fairer to do this. After all, pepperoni and Hawaiian are both pizza. It's just I would never eat Hawaiian. Anyway, subjectivity aside, let's look at multiplying by 10, 100 and 1,000 and dividing by 10, 100 and 1,000. If you've been practicing your 10 times table, you should know that 3 times 10 is 30. And then if I times that 30 again, we're going to get 300. And times it by 10 again, we get 3,000. Likewise with 0.003, if I times this by 10, I'm going to get 0.03. Times it by 10 again, I'm going to get 0.3. And I times it by 10 again, I'm going to get 3. So what is actually happening here? Remember how I said that there was like an imaginary decimal point after the unit? Yeah, so this was the unit on the column diagram on the previous page. I'll just go back to it quickly. This one. Yeah, the decimal point is immediately after the unit. If we go back now to this, when you times by 10, we've got a 10 and a unit, and the decimal point is now here. So it has shifted 1 hop to the right. Similar deal when we times by 10 again, we generate hundreds, tens and units, and the decimal point has hopped another place to the right. Finally, thousands, hundreds, tens, units, decimal point has hopped another place to the right. So a way of thinking about multiplying by 10 is the amount of hops the decimal point is going to make. It's going to go 2 spaces to the right and finally 3 spaces to the right if you multiply it by 1,000, because timesing by 10 3 times is the same as multiplying by 1,000. That's the same as multiplying by 100. Similar deal here. You can see that with timesing by 10 once, the decimal point jumps to there. By doing it twice, it jumps to there. And finally, by doing it 3 times, the decimal point is after the unit. You could jump straight from this number to this number by moving the decimal places 3 hops to the right. Okay, so if I do that, it goes 1, 2, 3. Okay, that's literally all that's going on when you're multiplying by 10. Dividing by 10 is the opposite way round. The decimal point is again where it's shown after the 3. Except this time, by dividing by 10, the decimal point goes to the left. So I will get 0.3 here. And then if I do it again, it's going to be moving to the left again to 0.03. And then if I move it again, I will get 0.003. Similar deal here, moving the decimal point to the left gives 0.03. Moving the decimal point again to the left is 0.003. And then finally moving it again to the left gives me 0.0003. So division means dp goes left. Multiplication, it's going right. So you're generating smaller numbers when you divide by 10, and you can go straight from the 0.3 to the 0.003 by doing 3 hops. 1, 2, 3, left. You could fill that in 0.0003. Yeah, there's going to be a 0 at the front there, which is the number we've got here. Okay. I hope that's been helpful today. Another slide for you to help practice on moving the decimal point left and right here. I think that's my last one on this video. I'm going to include these slides along with some practice questions on multiplying by 10 and dividing by 10, and have a go and see how you get on with them. Great, we'll leave it there, and I will see you on the next one.